It's now my pleasure to welcome Karim The bault, who is Associate Professor in the Department of Philosophy at the University of Bristol, and also a member of the Munich Center for Mathematical Philosophy. Professor The bault is an expert on philosophy of physics, and his main research focuses include the problem of time in classical and quantum theories of gravity, as well as black hole physics, quantum cosmology, the arrow of time, and the foundations of general relativity. Today, Professor The bault is going to talk to us about cosmic higher speculations and the arrow of explanation. Professor The bault.
Thank you very much, Michael. And it's a really great pleasure to be here. I think this the concept for a workshop, mixing these areas, it's really, really wonderful. It's something I think we should kind of put strenuous efforts within the academy to keep these links between, in particular, I think, for like philosophy of contemporary science, ancient philosophy, contemporary physics, and history. I mean, in many ways, these subjects for so many years were entwined, and it's a relatively modern phenomena for them to become, to some extent, disengaged, which has been, I think, hugely detrimental to all of them. That said, I will claim a large degree of ignorance of history of philosophy and history of science, but I will try and, by the end of the talk, at least forge some links to some of the contexts in which I want to talk about, to some historical contexts. I'm going to focus more on methodological issues than anything else. But the kind of context is really a discussion about time and how we should understand a particular type of causal problem and causal reasoning within modern cosmology. And this is based on work with a student called Will, and it's also part of a kind of British Academy fellowship project that I'm working on at the moment. So what I'll do briefly is just talk about a kind of quite simple idea that I wanted to explain, called the arrow of explanation, and just how it fits into the context of relativistic physics. I'll explain what I call the causal explanatory problem for Big Bang cosmology, which is usually called the horizon problem, but I think, in fact, this name captures it better. And then I'll look fairly briefly at two modern responses to this problem: the orthodox response in terms of something called inflationary cosmology, and a less orthodox response in terms of something called Big Bounce cosmology, which has a relationship to some of the models that Julian talked about as well. I'm going to make this. I'll then kind of return to this idea of connections to the early modern period and methodological issues at the end. I've endeavored to make this an entirely, or almost entirely, non-technical talk with no equations, rather with diagrams. So I will gloss over a few details, which hopefully will allow everyone to kind of follow the key ideas without getting buried in the maths. So let's start with the very basic idea. I find if I see myself while I'm giving the talk, it makes it extremely distracting. Okay, much better. So the idea is the arrow of explanation. So very simple idea. So if we have an explanation, we usually kind of label the parts of the explanation, the explanans, the thing doing the explaining, and the explanandum, the thing being to be explained. So we might imagine a simple explanation which consists of two explanans and one explanandum. This and this explains this third thing. And we usually think about this, I mean, often, and particularly in a classic philosophical science way, as involving a law and an initial condition and then some kind of result. So we could say gravity acts attractively according to Newton's law. The ball is given a subcritical initial velocity, i.e. we throw it up not fast enough so it escapes Earth's orbit, which explains the fact that the ball falls back to Earth. And what's crucial here is that there's an inference that has a structure that's temporal, that we usually think about the explanandum as happening after or at best at the same time as the explanans. We don't consider explanations in which the thing to be explained happens before the things that are doing the explaining as being legitimate explanation. And I think this is a quite important concept, that where directionality comes into physical reasoning without there being an explicit arrow of time. As Michael said at the beginning, it's often been quite mysterious in physics how to understand the role of time as a directed concept in a context where the laws are all time reversal invariant. And I think one kind of way of trying to understand it is that if we're using science to do explanatory reasoning, there seems to be a directness of explanation. And so I'll talk a bit about this a little bit later. The problem of the kind of tension between a requirement of explanation and a requirement of directedness. But let's just leave it in the background as something that we take as given for the time being. So how would this work in the context of a kind of not a single explanation, but a kind of broad drawing up of the kind of block of the universe into different regions? And so if we think about a simple diagrammatic way of describing space and time, where time runs from the left to the right and space runs up and down the page, we could then draw a line which represented the present, which would move along here as time passes, and we have the past on the left-hand side and the future on the right-hand side. And I'll be using these kind of diagrams as we go. And so just to reiterate what I said before, we'd then have the explanans in the past and the explanandums in the present, or at least in the future. And so we could think about just using a gray shadow effect to indicate the region which has explanatory power for the region that's on the right-hand side. So the things that explain what happens on this line and afterwards lie in the gray left-hand region. And this makes sense in Newtonian mechanics because there's no limit on how fast causal inference or influence can propagate. So if we imagine this is space, something that happened only a short time earlier, very, very far away. I can actually annotate this. So if we imagine an event here, and we imagine something that happened very, very far away, only a short time ago, because there's no upper speed of transmission, this is a potential explanans for an explanandum here. So the Newtonian kind of construction of the cosmos, there's no limit. As long as something's in the past, it can explain anything in the future. The contrast here, try to erase this. The contrast here, hold on a second. Get rid of these. Is with a relativistic universe, in which there is a finite speed of light. And so if we imagine an event here, the only things that can causally influence it in the past are things that propagate at the speed of light. So not every single, so we imagine the same event here that happens very far away, just earlier, this can't causally influence this event. It can't be a potential exponans for that explanandum. So we can think about the explanation or explanatory structure of a relativistic universe simply because of the speed of light as having this cone where the potential exponans are limited to regions of space-time in which you can have a signal travel between the explanans and the explanandum. Of course, most things don't travel at the speed of light, so we'd imagine them happening inside the cone. The cone is the limit of the influence that can happen from light-like explanans that are of the nature of light, to explanandum here. So anything that has mass has to lie in the kind of interior of the cone. Okay, so I mean, this very simple change in the nature of explanatory structure, combined with the expansion of the universe, leads to quite a difficult problem that to some degree, modern physics is still struggling to resolve. So let's first think about a way of representing the universe, the expanding universe. So if we draw a wedge, again with time going from left to right and space going up and down the page, if we imagine this arc at the edge of the wedge here as the size of the universe at the current time, the size of the visible universe at the current time, so that the sphere that we can, or depending on the geometry, but let's imagine it as a sphere that can be connected by a light signal from any kind of earliest time. We call this the patch. Let's say the patch of space corresponding to the visible universe at the moment. What we can then do is trace back, using Einstein's equations, how the universe would have behaved earlier and earlier time. And given the equations imply that the universe was previously expanding, we trace this back and back and back and back. And in fact, what happens is that in a certain kind of well-defined sense, the equations break down at some kind of initial singularity, which is the famous Big Bang singularity, which is actually the other half of the project that I'm working on, but I won't talk about that much in this talk. The other thing that's very important is that as we trace back the expansion of the universe, the causal past, the horizon that can have had causal influence on each of the slices of earlier and earlier size of the universe, shrinks more quickly than the size of the universe itself. This is particularly relevant because we've got observations that go all the way back to a quite early slice, this isn't drawn to scale, called the cosmic the time of the cosmic microwave background. So you may have seen these famous photos from satellite images of the kind of radiation kind of very low, I think it's about 2.7 degree Kelvin radiation that fills the sky. And so this observation has happened at a time when the horizon, the causal connectivity of the past of an observer was much smaller than the entire size of the patch of the universe at that time. And what this means is that because if we go back, if we assume that matter is kind of the same nature as the matter we experiment with on Earth, we find that the particle horizon, the area of causal connectivity in the past shrinks faster than the size of the actual universe itself, which means that, and as I said, at this kind of particular time which we have observations about, the CMB time, it's about 1,000 times larger than the size of the horizon, which is at this point the shaded region. However, and this is the problem, what we find is that the data, the kind of fluctuations in temperature and density across this patch that we see in the sky is almost perfectly uniform, which means that on the one hand, there are regions that are too far apart to have had to be causally connected, but on the other hand, these regions seem to be correlated. So this isn't violating any physical law. What it implies is that there's a correlation which has no dynamical explanation available within the context of modern physics. This is the causal explanatory problem or the horizon problem. We can find special ways of setting up the initial conditions of the universe such that the data can be accounted for, but that physicists, I think, almost entirely agree that this is in some ways problematic because there's no dynamical explanation for why it has this very special state, where you have uniformity across this larger scale that could have ever been causally connected in the past. I have a feeling I may need to speed up a little bit, but hopefully you'll be able to go through these diagrams quite quickly. So what is inflation? Inflation is essentially a postulated extremely early epoch, extremely early. So we're talking about many orders of magnitude earlier even than the cosmic microwave background and beyond anything we can directly detect, in which the dynamics are fundamentally different. In fact, the horizon stops growing slower than or stops shrinking slower than the size of the universe, and the size of the universe in fact shrinks quicker. So it relies on there being a novel form of matter, unlike anything that we've experimented on Earth or that we've directly detected, which produces a near exponential expansion of space. And this means we have this kind of special field, and we use Einstein's equations. We go back towards the Big Bang. The particle horizon, the area of causal connectivity, shrinks more slowly than the size of the universe, this original patch that we've been following. And so the patch size becomes smaller than the particle horizon at a particular critical point here. So what this means is that the region that has become the universe today was in fact causally connected in the past, right? Because there was this early phase we didn't know about, the region that's become the universe today, in fact, inflated from this tiny region, which was causally connected. And so the reason why we have this uniformity today is that the universe was seeded by a very small region, which was in equilibrium, and that explains the universe we see today. So there's something kind of interestingly odd about the structure of the explanation that the inflation provides. It involves this novel form of matter that's by necessity, unlike all other forms of matter that are postulated in the physics which we experiment on in colliders and that we have very good evidence for. It seems that we've solved the explanatory problem by using a highly speculative hypothesis. And it's not entirely convincing that that's better in principle than just having very special initial conditions and sticking with very kind of conventional matter. There's also a problem that on many models of inflation, it proves to be eternal. And in fact, the picture that I drew is not the picture that inflation describes. Rather, this would describe only a little bubble that kind of comes off from a like eternal multiverse of different universes, with our universe only having the features that it does contingently because we can only see inside the small bit of the bubble that we're in. Finally, because the expansion of space is exponential, it can't have started too early. Otherwise, arbitrarily high length scales beyond which we don't trust our physics at all, which we don't trust Einstein's equation in particular, would end up getting blown up, and the entire validity of the framework would seem to be undermined. So what's the alternative? And I mean, it was very interesting. I watched a video quite recently that one of the authors of the alternative solutions, Neil Turok, was saying that he was actually motivated to come up with the solution, an alternative, just because he wanted to kind of get people to interrogate the inflationary models and the type of things that they type of explanations and predictions they provide more carefully. So the explanation or the alternative in part comes from going back to the singularity. And by using quantum effects, either via string theory or other approaches to quantum gravity, the idea is that we can remove the singularity and move to a model of cosmology in which, in some sense, the universe tunnels to another regime, describing another universe. And one way of doing this, which I think is aesthetically more attractive, is to think about a symmetric bounce. So a universe which has essentially the same features as our own, but coming out as another phase beyond the Big Bang. And the interesting facet of these models is one then has this particular question about how we describe time. If we have completely symmetric in terms of the causal horizon, and we think about, we can think about this Janus idea in terms of the universe having a common past but two distinct futures. In this case, we wouldn't say that this is before or after the Big Bang, because the concepts of before and after, in some sense, are confined within these universes. And this will be particularly relevant when we get back to the era of explanation shortly. There's also models in which the bounce is asymmetric. The features of the universe before the bounce are different. And in particular, this the horizon, the structure of the horizon is different, which is quite salient to some of the things that those models can do. And these models usually insist that the arrow of time is in some sense beyond either of the two parts of the universe and is kind of superimposed and has a definite direction. And this really would be a bounce, and that this is a collapse and this is an expansion. In contrast, that the Janus universe would really think about this not being a bounce, but the kind of birth, the way that Chris Vutric puts it, the birth of twin universes. Again, the mechanism that they use to resolve the explanatory problem is quite different. The idea is then that the size of the patch that grew to the size of the universe at the time of the CMB is going to be smaller than the size of the horizon at some time before the Big Bang. So that means that generically this problem of causal connectivity is solved in a sense. I'll come back to why we might not think so in a second. There are also these asymmetric models that can resolve some of the other problems, or at least claim to resolve some of the other problems that inflationary cosmology can resolve, in particular to the smoothness of the universe. And the good thing is that these models usually avoid this particularly particularly low wavelength regime in which we would think the equations describing cosmology would break down anyway. So we're again, though, in a realm of higher speculation. I mean, if we think about the Janus universe in particular, whilst we have connectivity in the causal connectivity in the kind of very, very thin relativistic sense that there is a light-like path, a path that can be traveled by a photon that allows a kind of connection between all the regions in the CMB in the region before the bounce. Because we don't have this kind of no concept of an arrow of time that can be transferred between the universes, in particular if we have them pointing this way, it seems like the explanandum is now before the explanans in a certain sense, at least according to the arrow of time in the universe in which the explanans kind of the explanandum exists. There also seems to be a feature that the bounce is like a deus ex machina. It kind of sweeps in to resolve the problem without really without kind of obeying the logic of the universe that we're describing. And in the epichaotic models, this is to do with some high dimensional string theory, which we have very little evidence for, if any. So let me just briefly then get to the kind of more broader methodological context that I wanted to talk about, and then I'll wrap up. So I found this interesting concept in some early modern work called a cosmographical explanation, which seemed to have a nice resonance with what the way I was thinking about these cosmological models. So cosmographical explanations, in some sense, understood as founded on the natural philosophical analysis of the relation between the heavens and the earth. And in the early modern period, this was a contested space with, for example, an Aristotelian cosmography founded upon the fundamental difference between the two realms, which we heard about a bit in some of the previous talks. And in contrast, a kind of revisionary Cartesian cosmography founded upon the fundamental continuity between the kind of form of matter in the terrestrial and superluminary realm. And so there's I like the idea that in this kind of transition period of early modern natural philosophy, it's exactly the kind of relationship between these two different realms that becomes the area that's contested. And I think this is there's an interesting parallel with the context that I'm talking about. So fundamentally, the inflation and big bounce cosmology are based upon an analysis of the relation between a realm, a standard model matter, obeying the physics that we test on Earth, and that we kind of have conventional experimental and observational means to validate, and some exotic further realm that's characterized by things we can't directly observe, these inflatons, multiverses, or big bounces. And the nature of the explanatory reasoning in the space is ripe for contestation. And I think this is also exactly when these barriers between physics and philosophy start dissolving, and the kind of uneasy relationship between the subjects in the context of cosmology, which is an enduring thing, comes kind of up again. So I mean, and I think just as a more final thought about the discipline that I work within, philosophy of science, philosophy of physics, I think it's very noteworthy that it's exactly in this regime, in this domain, where the debates between the physicists, and particularly the most kind of well-known physicists defending the bouncing and inflationary models, these debates take on a very kind of explicit methodological character. And there's a number of papers really digging into the kind of philosophy of science arguments from a physicist's perspective that have been published recently about precisely the kind of contrast between these two approaches. It's also worth noting that this is also a context in which there's shifts in how we should understand empirical reasoning. And so as just a plug for some of my many kind of very outstanding colleagues who've been working in this area for the last 5 or 6 years, it's exactly, I think, the right thing that philosophers of science get engaged in these debates, exactly where the physicists are not always adequately using styles of philosophical argument and reasoning. And so I think it's a very exciting parallel between earlier phases of natural philosophy and earlier periods in which the methodological character and relation between different systems of reasoning, explanation, and the role of empirical evidence changes, that kind of should spur us to reintegrate historical, philosophical, and scientific modes of reasoning. And so I think that there's much work to do that, but it's a really worthy cause, and I think fits very well with the theme of the workshop. Thank you very much.